So I'd now like to introduce you to our fourth innovator, Mr. Frank Wang from NanoTune Technologies.
I'm very honored to be back to Florida after 2 decades. 1988, I graduated from University of Florida in material science and engineering department. And today, my best friend, one of them, in my class in University of Florida, just sit down over there, Martin Wilson. He, amazingly, he worked for U.S. United States Alliance for 2 decades. Also, after he graduated, so that is my honor to be back and see my friend here. I did see him for 2 decades, and he worked just nearby here, next building. Just amazing. Okay. So this technology was developed in University of Florida. At that time, I am under the Star Wars project, the Reagan era. So this technology truly developed in University of Florida, and now it takes to commercialize something. At that time, we tried to make the space very light glass for the laser light relay to shoot down the missile at that time. But now this technology is truly something. So I will report to you and see what is going on. So far, this technology is very interesting, and now we are getting into revolutionizing the energy storage. See, that when in the 80s, from 80s, we are doing the silica, SiO2, and now we are doing the carbon. And the carbon thing is for conducting material, and the silicon is for data storage or that semiconductor area. So today, I just try to let you know my work is try to replace this lithium battery. See, this is the lithium battery. Okay. You know, the lithium battery was developed in at that time, 70s, Beatles, okay, and Americans are wearing, the bell-bottom pants. See. And the people developed this lithium battery. It's already 40 years, and people love it, people hate it, and now NanoTune is trying to take you to next generation of energy storage, a little bit more close to the solid state storage. Data is a solid state storage. It's one piece, one big piece, grow the silicon wafer ingot to cut for data storage and follow the Moore's law. Moore's law is every 18 months, double, 2x, 2x, 2x. Very miserable. The lithium battery, the chemicals, it doesn't follow its way. The improvement is very miserable, a few percent a year. So that people are suffering. So now before we say NanoTune, Intel inside, right? Intel person here, Intel inside. And now next generation, we will energy storage start with NanoTune inside. Will be solid state. And now we are moving from chemical to physical. It means, chemical reaction, doesn't matter what. Reaction is that, take 35% your energy, your solar energy, very difficult to harvest into your storage. But if you are stored in the lithium battery, 35% is the tax, like IRS tax you into the heat. You cannot use. And now NanoTune can provide you a new meaning of energy storage. It's like a water tank. Water tank itself, the tank itself doesn't consume your energy at all. Chemical reaction truly consume your energy, 35%. That is a problem. Yeah, so NanoTune here try to move from such a chemical reaction to the physical. Yeah, so ion, talk about ion, like sodium, like the ocean, NaCl. Na is plus, Cl is minus. So when we saw charged, everything separate. Separate into what? Into terminal, a positive terminal, a negative terminal. Energy storage, you got to have two terminals, right? Yeah, so once a whistle, go charged. So let's talk later. Our company was founded 2004 at the time for bioseparation, for water purification, and soon we are direct into energy storage by Perkins, the KP, Kramer Perkins. Yeah, so, but the water is huge, but technology is so wonderful. Our energy cost is only 1/4 of a reverse osmosis, but we cannot get there because the market are occupied by reverse osmosis. And our company just only a startup. Okay, so change the topic. Change to energy storage. Bingo. We got, I spend a lot of time in the Starbucks, okay? Cook up my business plan. Unemployed, okay? So 2007, in November, the last day of November, I got $3 million from Draper, Fisher, Gibson, DFJ. Yeah, at the time, Khosla himself also give me the term sheets, and I accept DFJ, $3 million. Okay, so far, the Series A is complete. So I have my partner, he graduated from MIT, and in the computer EE area, work with me. He's an application person, I'm a material person. Okay, so over 40 years of combined successful entrepreneurship and running the startups, particularly in the electro technology area and ultracapacitor application. So we are on the very good edge of the tremendous opportunities. So our vision, like what I say, in the future, we will run into the physics, from chemical physics, liquid state, okay? And we will move soon, we will get into the solid state. Solid state, the liquid state is deal with ions, electrolytes. Okay, so far we are doing electrolytes. And in the next 3 or 5, our R&D will go into solid state. We will deal with electrons. So to store the energy directly into the electron. And now we are store energy in the electrolytes, ions. Oops. Okay, so market opportunity, I believe everybody know, everything around you, your life, your hearing aids, your heart, the pacemaker, all rely on batteries. But this battery actually not so wonderful. Yeah, so you have better to have a wonderful something to do. Okay, let me to introduce you our way to make very simple. Okay, very simple. It's only 2 technologies. One is called NanoTune, tune the pore size. One is that you can tune the pore size to 1 nanometer. That is a NanoTune. The name means tune the pore size very precisely. Okay, the mode silicon mode. I can tune precisely to anywhere from 1 nanometer to 1,000 nanometer, no problem. Very, very easy to tune, okay? And it's a large scale of operation, okay? That is scary. It's like a kiln for a building. You make the bricks for a building. That's scary, huge. In 3 days, boom, and all done. Whatever you want in a kiln, boom, done. So that is a very, very scary operation. Okay, they're called a NanoTune and NanoCast. NanoCast is very simple. I can show you. This is a same mode. We make very, very thin, the thinner to 100 micron, or even thinner, 50 micron. And in our next research, we are into 25 micron, thinner and huge amount by Teflon mode. Teflon is hydrophobic. It doesn't stick, okay? So we can make a huge amount. So see, here's the water. I can suck this one. The way to suck the water in, oops. It will suck in 1 minute. Suck in how much? 3 times of the weight of the silica. Sponge. And this is a 15 nanometer, okay, 15 nanometer. So we suck in a liquid. So use this, we call it nanocasting. Nanocasting is a cast. You are carbon, conducting carbon precursors, okay, into the pore. And yin and yang, you know the yin and yang, right? Okay, so that is the way it is. Okay, so now the white become a suck in, become clear. It's in. And you can do the image, just image. The pore becomes solid, solid become pore. Deng. Okay, so now you know how to make this. And now, like a poker, like a pile of the poker card, very thin, and you put together positive, negative, and a film of aluminum powder ping pong ball in between become a separator. Boom, 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 and positive, negative become a book, or become a brick, and you can make a huge amount. Okay, that is scary. So it can put together, housing very easy, low by low. Initially, it's like a kiln operation, big, and now low by low. Put together, boom, 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 electrolytes in, everything in, and assemble together. Okay, so now we are growing. Cost-wise down, the manufacturing scale up, and that is our performance. So far, we already exceed 4 times or 8 times the Maxwell, the ultracapacitor, the powder like. They make a powder and glue together on the substrate, aluminum, very thin aluminum substrate. That is what they make the electrode. Okay, so now our monolith, nanoporous electrode, just dust them away. Dust the powder away by monolith, the name card size, the poker card size. The dust them away already. See, that is 8 times, and immediately we go to consumer electronics. And the next year, our R&D is already achieved 40. So next year, following year, we will start to replace that acid battery. They are all, that acid and the aluminum, the lithium are all chemical. See, that is our roadmap to grow. So soon, our limitation by ion could be 400 or 500. So that is, and now we need to transform Series A learning into B. We already complete Series A, and now get into the B. Okay, we need to gear up our quantity, quality, and every stability. So we need to scale up production to 1,000 a month to 10,000 a month. Okay, so what we need to have you to help. it's continued growth everywhere. R&D, the team, to strengthen our team, we are very thin now. So we truly need to be helped quickly, okay? And our market focus, we need to see which market we need to penetrate easily, okay? So of course, we need money, investment to share our dream. Okay, so let's see how industrial say to this. Maxwell already doubled ultracapacitor production this year, doubled. And Binoy Khosla predict A123 will not around in 10 years, okay? And the day of battery numbered ultracapacitor will power us into the future. Okay, so Elon Musk said, okay? So I take NanoTune from the laboratory to the market ubiquity, okay? And provide green, lighter, cheaper, safer energy store for everybody. And I believe you suffer, all the time, not enough juice from the lithium battery. And instantly charge, boom. That's what I can provide to you.
Thank you, Frank, for a wonderful, entertaining presentation. Before we begin question and answer, or questions, which I imagine you have almost an infinite amount of, let me just clarify a few points. This is a deadly, serious technology, and this is something I really, really feel like as a group we need to understand. Frank and his partner Katie have invented an ultracapacitor that is cheaper than anything else on the marketplace right now, that has a higher energy density than anything else on the marketplace right now, that is capable of instant charging. This is a sort of a ridiculously important point. You put it on a charge pad and the battery charges almost instantly. It produces no heat. It has a broad range of use in terms of temperature utilization. Each single unit can take up to 1 million charges. I don't know how many of you have a cell phone that is now on its last legs, or your laptop that is dying. Imagine a laptop that is instantly and infinitely chargeable. This is what is in the game. We're talking about an ultracapacitor that has a completely flexible form factor. We can make a car out of these things. I just want you to think about that. We can make a car shell out of ultracapacitor. It will be a battery. The actual frame of the car could be the battery that powers the vehicle. In terms of structures, in terms of spaceships, in terms of anything, this is an incredible revolutionary technology. So with that, Frank's partner Katie is going to join us on question and answer. I would really request that we keep the questions good and simple, and in terms of technical detail, these guys have a superabundance of information. We can get it to you. Okay, Diana, and then Guy.
So I always thought the problem with ultracapacitors was that they discharge almost as quickly as they charge. So what's the issue there?
To you. Yeah.
And let's sort of bounce forwards and back.
Okay.
Let's give Katie a chance.
Yeah, okay. In this case, I can, because technical.
Okay.
Technical.
Okay.
Yeah, you see, the ultracapacitor you use is 5 watts hour per kilogram, very little juice. It is like your water tank on water tower on your home somewhere. It's very low juice. Okay, ours is huge. It's like a Hoover dam, huge. Okay, okay. So very quick you discharge it, use up because you have a tower, water tower or ultracapacitor tower, not hot enough juice. So you use very quick. But when we can build a water tank on the mountain, a huge one, okay, you can use a lot. And water, it's a high voltage, it could be 400 volts by in parallel, in series, altogether, hot there. Okay, so the same thing.
Okay, to quick answer your question, I think we would discharge in 24 hours 40%. So we still have 60%. Compared to the lithium battery, I think we are equal.
Okay, great. Other questions? Yes, Peter.
You talked about using this for car bodies or for other
Oh, yeah.
structural elements. How strong is the
Oh
material?
yeah, now we are evolving. Our material so far is amorphous carbon. Amorphous carbon doesn't have enough strength. And now in our laboratory, we already see 20% of our amorphous carbon get into the shape distort. We call it the shape distort. Yeah, you see that's the sentence, resulting in a monolithic, nanoporous 3D interconnected shape distort graphene-like structure electron. Graphene, graphene promise you a lot. Strength, and it's all connect 3D, it's polymerized. Well, it's polymerized, wow.
And
Okay.
Katie, anything that you want to sort of...
I think right now, amorphous state is definitely brittle. But we have about 22% graphene. In the long run, we are shooting for around 50% graphene or graphene-like material. So that will be strong. Okay.
Good. Guy?
What's you showed the energy density, compared those on all the three technologies. What's how does that compare for sales price?
Oh, yeah.
At those levels?
Yeah, I have a Pendex. Okay, this is what now compare with the $6,000 compared with currently powder-based Maxwell's. We are about 3 to 4 times already compared to penetrate in the traditional, conventional ultracapacitor area. And soon, because we don't have the manufacturing, everything to become a commodity, drop. You see, this is red line. Red line is a lithium battery today, $600. After 2020, will be dropped around, about 150 because commodity is a percentage drop every year. And now we are get in, boom, and we are very compatible in 5 years to go.
I think in summary, in 3 years, we'll be competitive to the lithium battery price. Volume-wise and also the weight-wise, we will probably 1/3 smaller. Yes.
What's driving that cost reduction? Is that purely scale, or is that additional R&D involved?
I think the key is the manufacturing process. Our manufacturing process is a kiln-like process, like a brick. When you do brick, you have the mold, and then you put the mud in there, you come up with a brick. Similarly, we're using that kind of process. We have one Japanese big company has that kind of process. They're currently producing carbon jet, and we're using that facility. Okay, so that will help us reduce the cost in terms of producing electrode. And then the rest will be similar type of packaging. We were using prismatic packaging versus the current one is cylindrical packaging. Will be cheaper. And of course, the scaling will make it cheaper, yes.
So assuming you get funding, what are you doing in the next 12 months?
Yes, we would do the pilot production. Pilot production means that we like to produce 1,000 to 10,000 per month sales, which we then design in with some of the manufacturing product so they can do market trial. Once they do market trial, they're successful, will become 10 million pieces per month. And we'd like to get 3 PO after that.
Can you tell us, do you have any information about production facilities? Have you had some news recently in that area?
We actually have a number of state interests to have us bring the manufacturing here. For example, in California, I have Governor Rick Scott call me that if we, Florida, Governor of Florida, Rick Scott. If we can set up manufacturing facility here, they will give us certain grant and also approaching a number of different states.
So it seems like most ultracaps, and yours included, lose a fair amount of charge, as was alluded to, so that the best applications are things where you're either frequently connected to the grid or you're a hybrid system with a battery, depending on the application. What's the initial target application?
Okay. We would target initial to a smaller ultracapacitor. For example, hearing aid, right now, every 1 or 2 days, you need to charge or change the battery, and we can using that as a rechargeable. Okay, our initial application will be in this area, smartphone, smart tablet, which it will be smaller, using for pulse energy, support those. And we also have number of auto company working with us. They said that if it's 40 watt-hour per kilogram energy density, the entire HEV will be designed along this line. Entire hybrid EV, HEV. Hybrid electric
HEV.
vehicle, yeah.
I think we have time for one more question. Two more questions. One.
Just out of curiosity, how, for the material you've produced so far, what are the size ranges you've been able to fabricate in the lab, and how big do you feasibly believe in the next 1 to 2 years you could actually fabricate scale-wise?
Okay, the current size you can see, we are flexible. We can produce the phone size, the screen size. We also can produce 9-inch, the iTablet type of screen size. Our production is using the mold. So whatever size you want, we can produce. But I think we'll try to limit it to around 9-inch, 12-inch, 14-inch, around that kind of size. Yeah.
And we'll close out with David.
What size product are you going to make? You said you're going to get 1,000 to 10,000 a month. What are you making?
Okay, for example, for this, the requirement is around 650 milliamp, okay, size of cell. Okay, for auto industry, I think will be CD-ROM size. Each one would have a different cell packaging, but I think the total one could be 16 kilowatt-hour kind of modular, and for solar will be 3,000 farad or 350 farad.
I'm sorry, I didn't understand the answer. What would you make if you?
Oh, you mean the electrode?
Yes.
Okay. Electrode itself will be depend on the application. We have flexible form factor. So if you want to have application of this, you want to have the battery in the size of this phone, then you produce the electrode size according to this size of the phone size. If you want to do it on iTablet, then you try to do it in the tablet size, and you can have a number of pieces sticking together in the back of the tablet.
So there's a module size that you've picked?
Whatever we do custom size. We do custom size, but we try to standard some of the standard size, and then you pack together. In fact, we do have some of that. Yeah.
Can I take the microphone? Gentlemen, thank you very much indeed.